All right. Hello, everyone. It is super awesome to see everybody here. I'm very excited to start talking to you guys about MLflow, right? It is a life cycle management tool, to put it to put it at a very high level. But this life cycle management tool is something that is incredibly important and relevant to data scientists, machine learning engineers, and basically everybody in industry, right? And we are going to discuss the model registry aspect of MLflow, which is almost, I would say, the core of the lifecycle management aspect of what MLflow stands to provide. And the utility is absolutely incredible. So I'm extremely excited to sort of go over this with you all. So if there are any questions at any point in time, feel free to either drop it in chat or unmute and interrupt me at any point in time. That is perfectly okay. I much rather have this be more of a discussion rather than just me talking to my screen for a whole hour. But Jono will be there throughout the session to answer any questions, and he is an absolute expert at MLflow and model registry specifically. So there is nothing that he probably would not know. So with 243 million downloads and stars on GitHub, it is one of the most widely adapted open source tools for lifecycle management. It supports stuff like the parameters, metrics, and artifacts, in addition to providing a model registry with a deployment functionality. And we've integrated MLflow to DagsHub over 2 years ago, video configuration, remote MLflow server with built-in access controls that supports MLflow registry and deployment, basically everything that MLflow provides. We've dived into its internals, handle many of the specifics, and do a lot of the MLOps heavy lifting for you. And if you would like to follow through what we are going to work on today, please sign up to DagsHub using the link in the Colab notebook, and it will basically allow do a lot of the MLOps heavy lifting for you. And if you'd like to follow along, we will be using the DagsHub stack throughout the process. So I will give you guys a couple of minutes to do that. Just it should not take too long, so I'll say a minute and a half or something. While we wait, feel free to check out some of these memes. I think they're, but if they're not, feel free to let me know. Okay, I'll wait for like another couple of seconds. All right. And it's 30 exact. So all right, let's I guess move on, right? So on Pi Day, which was 2 weeks ago, we discussed MLflow experiments, runs, and logging parameters, metrics, and artifacts, right? So we basically went through an entire tour of MLflow and all of the functionality that it provides. And for our first session, we covered experiments, runs, and logging stuff like parameters, metrics, and artifacts. These are all incredibly relevant to us, and we were able to use MLflow to replace spreadsheets and Notion pages that we previously used to track our experiments with. And it effectively is a lab manual that automatically all of the experiments that we run, right? And throughout a machine learning lifecycle, or hyperparameter tuning, for instance, you have a lot of different parameters that you want to ensure performs at the best possible accuracy, right? order to tune these parameters, it is generally a lot of manual work to ensure that everything works properly. And through the hundreds of experiments that you would probably run to ensure that your model performs optimally, it is very easy to sort of miss out on a lot of information. And MLflow effectively allows the aggregation of all of this information as well as the active comparison of said information. So the dichotomy of experiment tracking within MLflow experiments is as follows. You can we have two major components. The first is an experiment, and the second is a run, right? And the concepts of experiments and runs are flexible and depend on your situation as well as your preferences. But generally, you can think of an experiment as a hypothesis you are testing while training your model. For instance, we can look at the optimal learning rate, right? And each experiment can have one or more runs. So you may hypothesize that your learning rate, your optimal learning rate is between 10 to the power of -3 and 10 to the power of -6. And you would have that entire question is your hypothesis or your experiment, and within your experiment you will run it iteratively for each of your expected or guessed, so 10 to the power 3, -4, -5, and -6, and these will all be 4 individual runs. During these runs, you can log your parameters, metrics, and artifacts that you want to keep track of and compare later on. So as I said before, when used this way, MLflow is effectively your digital lab notebook. In our previous session, we all discussed the various scenarios that are available in order to use MLflow. And these scenarios range from increasing levels of complexity, and with increasing levels of complexity, it also provided a significant advantage in terms of the scalability of the architecture. So we started off with just using MLflow and directly writing our logs to a file or a series of files inside a directory. We upgraded that to an SQLite database. Then we used a remote server, and but that basically takes us into DevOps land, right? And as data scientists, our focus should be on the data and not setting up our mechanisms for the data. So what DagsHub does is that it sets up the most complicated scenario that MLflow provides. That is the component diagram that we have right here. So the effective idea of this flowchart is we have these 4 major components. The first one is the local host, the machine on which you would actually perform your training. So you need to have a powerful GPU on said machine. Hopefully you can train something that is really, really powerful with it. There is a remote host that contains a tracking server. And this tracking server is basically a server that communicates with the local host using a REST API. And it communicates the following information. It communicates information about the runs, the metrics, parameters, as well as specific tags that you would assign to a given run. It also logs the models, images, configuration files, and any other additional artifacts that you believe are relevant to your experiment. And whenever any sort of during the training run, what effectively happens is your local with the remote host and provides all of this information, and this information is then aggregated and stored efficiently by the remote PostgreSQL server or the S3 bucket in case of model artifacts. And as a result of this, you are able to look back on all of the experiments that you have run and evaluate which combination of hyperparameters or experimental setups works best to provide the most optimal set of weights for your given optimization routine, right? And DagsHub basically provides this entire remote MLflow server with every single repository for free. So that's the recap of everything that we spoke about over our last session. So if you were not there for that session, you basically are caught up. There is still some more information, and that has to do with using the MLflow API to actually log information. But for the extent of today's workshop, where we will discuss the model registry, we don't need to really worry about that. But if you do want to check it out, we upload that to our YouTube channel in the next couple of days. So feel free to check that out. So today's agenda, right? Let's talk about what we are going to cover today. In this workshop, we're going to expand your MLflow knowledge and learn about the model registry. You will and register models to the registry, load models from the registry, deploy a model to Amazon SageMaker using MLflow's registry, and finally, you will learn to create a Docker image which can be used to deploy a model anywhere. So your endpoint delivery stage of your lifecycle is what we will focus on today. So let's get started. So the first thing is, why is deployment important for us to learn? Machine learning models are only valuable when they are deployed to production, right? So if no one has state-of-the-art machine learning model that we develop, then it really does not matter how good it is, because its value is derived from its use, right? So the model that can solve every single problem that humanity has but can't use it, it's not very useful to us, simply because it's not something that we can use, right? It's only available in theory. So that is why being able to deploy models effectively is very crucial to us, because if you as a data scientist develop a model that is the state of the art, and your deployment team or your development team or your DevOps team is just using a Bayesian model to I don't know, classify spam, then it's not the most efficient use of resources. So look at the model registry. The registry is a centralized store for your models. It provides a place to put models related to experiment, to its model versioning, as well as stage. By keeping track of these things, MLflow makes it easier for you to determine which model you need to deploy in which environment or which scenario. It makes the whole process less prone to error. So the MLflow registry has a couple of important concepts. The first one is that of a model that is created from an experiment. It is logged using the MLflow.framework. So you would specify what framework you are using and use the log model. The second is that of a registered model. It is a model that is just registered with the MLflow registry, right? It has a unique name. It contains versions, associated transitional stages, model lineage, as well as other relevant metadata. The third is model version. So registered models have more versions. The initial version is 1, and that version is auto-incremented when new models are registered using the same model name. The fourth important concept is that stage, right? It is predefined as staging, production, and archive. So these are the 3 stages that a model can have. Currently, custom stages are not supported, but there is an open feature request in order to add this. I think this is from 2020. So while it is not technically closed, it still is, or while it's not really in development, it's still technically open. So all hope is not lost. But the idea model stages is that every single model, or within your life cycle, starts at the point where it is experimental. It is not being verified, or the approach has not been verified, so you do not know how well the approach is going to perform. At some point, you are convinced that everything works, and you deploy it to your production. And once you find a new fantastic state of the art that is performing even better than your current production model, you will probably that in favor of the updated state of the art. So model stages basically allows the organization of resources using tags effectively. So the fifth and last concept that is critical to the MLflow model registry is our annotation descriptions. So you can use Markdown to annotate either the top level model or any individual versions with information that you think is relevant for the rest of your team. So that is another useful feature that MLflow Model Registry provides. There is a subtle difference between logging and registering a model of them in terms of their purpose. So logging a model is very relevant for reproducibility because it logs all of the parameters and the metrics that we obtain from the training procedure. Registering a model on the other end is important for production. And however, both log and register a model in one single step using MLflow's API. And just as importantly, not only can you log and register models, but you can load and deploy them as well. So this is a very, very useful graph that describes the entire process. We have the MLflow tracking server, which is what we spoke about in the last workshop, where we can know where track parameters, metrics, artifacts, metadata, as well as the model itself. And today we will be focusing our discussion on the MLflow model registry, where we have models in all of these different stages, and you can identify this almost crossover point in staging and production, handoffs to deployment engineers, right? So data scientists will be the ones that are performing the experiments and setting models as staging once they are satisfied with experiments that perform well. Your deployment engineers will set up a bunch of unit tests that are important to ensure the model doesn't go absolutely haywire when you give it a confusing input. And once they are convinced, they will probably move that to production. And then when they get a new state of the art that they find performs better than the previous or the current model that is in production, they will deploy it. So that is your entire sort of life cycle in a single diagram. So so once you understand how these together, you can even change specific aspects of models that you have registered previously. So you can change stuff like the model name, stage, which is very important, and model tags and attributes. Of these, number 2 is possibly the most important. That is because that is how you will has been moved from staging to production and keep your entire organization on the same page regarding the current state of your model or experiment. The next useful feature is that of searching. The project runs, the more experiments, runs, and registered models you will have. And keeping track of all of them would be an absolute nightmare without the ability to search. MLflow already addresses this problem and includes Python APIs to fetch a list of all of the registered models, as well as search for models by either exact or partial name using a SQL-like query format. So that simplifies everything to a significant amount, because SQL is very much a human readable language, and it is very easy to understand or pick up SQL if you haven't used it already. And SQL is also incredibly efficient, as a result of which you are able to use SQL even when the number of runs and experiments and models that you have registered is incredibly high. So it is very robust to scaling, which is also incredibly important to us. So the next concept that we will talk about is model serving. So MLflow offers options for both serving and deployment. The difference is subtle, but it is very important. Model serving uses the current machine, whereas deployment can be just any machine. Model deploying is also dependent on creating a Docker image. And we will cover the Docker image and its utility also within our session today. So first things first, we have model serving, right? So you can serve your registered model locally using the command, using the CLI command MLflow Server. By default, what it will do is it will serve a REST API version of your model on port 5000, and the inference endpoint is localhost port 5000, and the invocation Behind the hood, what it is doing, what MLflow is doing, is using Flask to create the web application, and you use curl requests to send as input the whatever input your model will take, such as an image or text-based information. This is probably dependent on your model. If you have a graph-based neural network, you will probably provide as input to the model a graph, and it will provide as output the inference in a JSON format. Model deployment, which is similar to but different from model serving, is basically deploying or serving a model to a or at a remote host. When you're ready to deploy a model, there are a few built-in options that MLflow provides. It has built-in support to deploy Amazon SageMaker as well as Microsoft Azure. There are third-party plugins that are available if you'd like to deploy to another backend like Redis AI, TorchServe, Algorithmia, or none of these services are your personal or professional preference for hosting your models. Of very interesting and relevant options. The first is to write a custom deployment plugin following the examples above, or use MLflow to generate a Docker image which wraps your model in a REST API. And what that does is it allows you to basically serve your Docker container because it is very straightforward to do that, since most backends or most cloud backends definitely provide the option of serving a Docker container simply because it is industry standard today. By creating a Docker image, you have the ultimate flexibility to take your model absolutely. The Docker image uses Nginx and Gunicon, and that effectively allows it to parallelize model deployment. As a result of which, you are able to basically have parallel queries that you can request a Docker container, and the Docker container will basically not slow down if you have like 500 requests at the same time, because all it would do is create multiple threads. The only real restriction is the amount of compute that you have on hand.
Jinen, really quickly, I'm getting a request to zoom the screen ever so slightly.
Is this good?
Yeah, I think that should be better. Thank you.
Okay, awesome. So there is this meme where we have one developer going, "It works on my machine," and the other developer says, "Okay, we'll." And that is how Docker respond, because it uses the same user space, right? Which is user space within the same kernel itself, which is kind of awesome. But if you're unfamiliar with Docker, there is a really nice beginner-friendly tutorial. For the time being, just know that it's a way to build, test, and reproducibly deploy applications using containers on a variety of hardware and software. It's effectively a very robust virtual machine, which is, I think, another very simple way to look at it. So it doesn't matter what you run a Docker container on, because since everything is containerized, that container environment, and that way you can basically deploy anything anywhere and not have to worry about installing or configuring packages and stuff like that. We are done with more of the theoretical aspect of things, and we'll begin our deep dive into the actual technical concepts the applied nature of of these concepts. So I'll take a break for a couple of minutes. Now would be an awesome time, and we can probably have a discussion around those.
We have a couple of questions so far already, and the first one is: do you think MLflow replaces the research log, or are they complementary tools? If you think MLflow replaces the research log, how do you keep the context of the experiment in MLflow?
Yeah, no, I lost you after. If you think they can replace the log.
So do you think, can you hear me now? Is this better?
Yeah, I can hear you now.
Okay, so do you think MLflow replaces the research log, or are they complementary tools? If you think MLflow replaces the research log, how do you keep the context of the experiment in MLflow?
Right. believe that it replaces the research log because I no longer used any secondary method of logging my experiments once I started using MLflow. The MLflow Python API has a log text functionality wherein you can basically provide a series of contextual information regarding your run or whatever experiment that you are attempting to evaluate, and that provides the contextual information that is relevant. And the other thing is that MLflow also has tags, and those tags allow for you to set up sort of labels for your experiments, and you can categorize them very easily. So with the combination, relevant to sort of swap it out with, or like to keep a log in a complementary state. So a Notion document that
Jinen, your internet seems to be a little bit unstable. Do you have an opportunity to change Wi-Fi or anything?
I don't. That won't be possible. I'm in university
Okay.
Wi-Fi, so okay. Is this a little bit better? I'm using a different connection.
No, that seems to be just as bad.
Yeah, it's the same. I apologize.
Okay, well, we'll just. I mean, it's been okay. It's just not ideal. Let's just continue, and if we miss anything large, then I'll just ask you to back up a bit, if you don't mind.
Yeah, absolutely. And are there any more questions that you want us to cover? And if so,
there was
do you think-
another one. Yeah, someone would like to know your opinion on the scalability of MLflow Serve, and when should I choose something like RayServe? I did not do those experiments. I don't know if you did.
Do you think you could take the question because it's breaking too much on my end? I will try to figure out
Sure.
something in the meantime.
All right. So I am actually. So I did not. I have not played around with RayServe myself. I have used MLflow Serve, or actually the deploy version, to basically work with Label Studio. So I've used MLflow to deploy our machine learning model so that I could connect it to Label Studio, so that Label Studio could send data to the model, and the model could run predictions on it and send the information back to Label Studio. And for that, it's obviously a very simple test case. I mean, I ran, I think, something like 10,000 data points through it, but it's only one user running 10,000 data points through a model, which is not really stressing it as a server. If you are concerned with the scalability of it, there are, let me think. What you could do is you could actually create your own web app. So don't use the built-in MLflow REST API wrapper. You could create your own REST API or your own structure around it, but you can still use MLflow to load your model from the registry and use it that way. So in that respect, the scalability is not in terms of how many connection requests can you get through your web server. It's just how fast can the machine that you're running on run the model via what you've loaded from MLflow. So that's potentially a possibility. Unfortunately, I don't know RayServe, so I can't talk to using that.
Okay, I killed my video, and hopefully the internet gets a little bit better as well, so that we don't have to worry about broken frames. But if that does happen, please let me know, and I will roll back to whatever the last checkpoint was, where the internet was fairly understandable or usable. Okay, So let's move forward. Let's discuss our sample project that we basically went over through the last workshop. But what we were basically doing was working with a small sample model that can classify whether a video game frame contains one of either Mario or his arch rival Wario. So we have the a nice little graphic that shows have Mario on the left.
Again.
Oh, come on. Where was the last point that I was
you were showing the Mario versus Wario graphic, that one, yeah.
Okay.
So I think it's interesting. So.
All right. So, okay. In our last workshop, we were working with a small sample model to classify whether a video game frame contained one of either Mario or his arch rival Wario. So it's a very straightforward CNN that we are looking to implement, wherein we take as input a video game frame, right? And this video game frame is completely in grayscale. We have Mario to our left and Wario to our right. And our objective is to basically predict whether the image contains Mario or Wario given the input image, right? So to get started with the project setup, first, please fork the base repository. So if you open the link over here, I have it open, but I could open it once again nonetheless. But this is our base repository on which we will get started. And yeah, so if you'd like to follow along, please fork the repository. You can change the name that you would like to assign, but I will keep it the same. And in a second, my own version of the base repository on which I can record. And this repository that I had just created should have its own MLflow on the backend. So that side is basically taken care of. Next, we are going.
Jinen, just a second. I just want to repeat that because a keyword was missing. When he forked the repo, his repo has its own MLflow server automatically connected to it.
Right. Yeah. Internet connection is unstable. Okay. Right. So next, what I'm going to do is basically install the DagsHub client, and the DagsHub client will basically allow us to allow for ease of use with the interfacing with our MLflow repository or our MLflow remote host, because it will allow authentication processes that would otherwise be a bit iffy because we'd have to enter our password manually. So in here, enter your username that you used to sign up. In my case, it's my name in lowercase, and the email that you used to sign up for your DagsHub account. That is my email address. So you can enter the name of the fork repository. So if you've changed this, you would probably want to change it to that. But since I let it be the same, I don't have to make any modifications. So that is that basically sorted. Next, I want to obtain an authentication token for improved account security. So all I would do is run this tab, and what it would do is create an OAuth request with the DagsHub server. And once I press accept, that's basically have the DagsHub token right there, and we will basically be using that in order to interface with the authentication restricted components of the MLflow server, so that way we can maintain the security of our repo. So now we have our prior sorted, we can clone our. So first things first, we configure Git on the Colab instance with the email and the username. If you would like to change that, feel free to do so. But yeah, that's basically this is just for Git specifically, not really the remote. So if this information is arbitrary, that's also actually technically all right. Next, what we are going to do is clone set repository and cd into the directory. So if I open up the tab, I will see the Mario versus Wario repository that we have over here in this Colab notebook, and we can basically take or use it from there. So next, let's actually begin to install MLflow. MLflow has several types of versions, and each of them have different ranges of support and features. The base MLflow is what we are going to use today, and you could install that directly just by saying pip install MLflow. If you want to use MLflow with its additional libraries and third-party software, you can do that by providing the extras flag, and it will install all of the extras for us. And if you have a resource restricted system, you can also install a lightweight version of MLflow that's called MLflow Skinny. So for our purposes today, all we need is MLflow, and that's basically what we are going to install. And that should take not more than a moment to set up. Next, what we are going to do is we are going to configure our environment variables. So the first bit of information that we need is the MLflow tracking URI. This is basically this link over here in our experiments tab. Under remotes, we get this tracking remote, and it allows us to access the base MLflow remote, which basically contains all of our experiments. Right now, we just initialized a new repository, and this new repository contains an empty MLflow server, of course, so we cannot see anything here, but we will populate this chart very, very soon. So within our environment variable, what we are going to do is just specify this URL, and we are constructing it using the username and repository format. But if you want to manually implement it, that is okay too. So we have in addition to this, we have our MLflow tracking username, which is the same as our DagsHub username, and the MLflow tracking password, which is basically our token that we will use to authorize any information. So finally, an important thing that I would like to mention is that it's recommended to not set up the tracking URI as an OS environment variable, simply because the environment variable does not necessarily, because the projects basically change with your directory, right? So multiple project management becomes a lot more complicated in that instance. So it's recommended to directly or manually enter our information for the tracking URI in our scripts, and the environment variables regarding the username and the password, they can be environment variables. That's perfect. So once we are done with importing our environment variables, we can simply import MLflow, and that sets up our repository to notebook to actually use the MLflow library. So to get started, let's run the following training script. It will train a model, log parameters, metrics, and log the model artifacts. So I will get this to run, and while I actually run this, I will go over the actual training script. So in the training script over here, what we're basically doing is we are specifying our MLflow imports. We have the get dataset function, and what it really does is it gets the train, validation, and test dataset generators, and from the dataset generators, it calls flow from directory. So that basically sets up all of our training data. We have a get model function. What that does is it defines a sequential neural network with three convolutional neural network, three convolutional layers and one hidden fully connected layer, with a final prediction layer with the sigmoid activation function. We compile that with binary cross entropy as our loss and report the accuracy as our metric. We run it with an image size of 128 by 128 pixels. Our learning rate is 10 to the power of -3, and we run this for 5 epochs. Within our actual training script aspect, right, once we finish defining our constants or hyperparameters, we have the experiment ID, wherein we get the experiment we have defined arbitrarily. And within this experiment, it starts a run. It performs the model training itself. It fits the model, evaluates the model, saves it to the model's directory. And once that is done, it logs a set of artifact, which is the model's directory itself. And
Jinen, can you go back a couple of lines?
Yeah.
Can you go back a couple lines to the log where you're logging parameters, I think.
Okay. All right. So for logging parameters, what we are doing is we are basically manually logging a couple of parameters. So there is the log param function and of key value pairs. This is something that we covered in the previous workshop, but we basically artifacts and the general log text where we can add contextual information to our MLflow backend. Once we do that, that's basically our entire training run completed. And we can see over here, it has found the images, it started training the model, it trained our model, and we got an amazing 37.78% accuracy, which is kind of sad actually, because if we inverse the predictions that are made by the model, it will actually be more accurate since it's a binary classification problem. But we move on. Our focus for today is registering the models, so that's what we'll take a look at. Next, what we'll do is we'll run a script that gets the last ID for the current experiment named Mario_Mario and stores it into an environment variable called run ID. This basically, yeah, that's it. What it does, we specify the environment variable that we want to save it to. So if I can quickly open that script as well, what get last run ID does is it first sets the tracking URI, pulls it from the environment variable that we set. What it does is, what this function does is it first picks up the experiment based on the name that we provide as an argument. It initializes the MLflow client and searches through all of the runs within the experiment. So it searches through all of the runs that exist within Mario_Vario in our case. If the length of the runs is 0, which means that there are no runs that it returns from the search, it will simply return none. Next, if it is able to find more than one run or one or more than one run, it will just return the last run that is with the search. And then we just return the ID for the last run that we have retrieved. Once that is done, we basically set it as an environment variable with input being the argument that we get right here. So in our case, this run ID, it sets that and we get an output that just confirms that everything ran nominally. So if I run this, what will happen is it shows us the hash of the run and it saves it and that it saved the environment to the environment variable run ID. So if we run this command line, this command from MLflow's CLI, what it basically does is it pulls out the last experiment that we get. So we can identify that it is exactly the same. So this is just a verification or a sanity check for us to ensure that everything is functioning nominally. So at this point, what we have done is we have saved the last run ID to the run ID variable. This will become very, very important later on. So this is just us sorting out a couple of important priors. Now let us discuss the methods that we can use to actually log models. There are a couple of programmatic methods that we can use to log models. The first is using MLflow.register model. And this is basically the Python API that we can call if we want to register a model after training. So if we have like in this instance, we have a model output. So if we open this models directory, we will see that we have our resultant output model, right? And in order for us to actually log this or register this into the model registry, we can use the register model function. And we here is where we actually use the run ID variable, right? We grab the run ID variable from our set of environment variables. We select a subpath name for this run. We select a name for the model to be registered with. So in this case, I want to set it as cool Mario model. And we can build or construct a run URI from these inputs. Then once we do that, we can call the register model function, providing as input the run URI and the model name that we want to set it against. So our run URI, as you mentioned previously, is just runs : / the run ID / and then the subpath itself. Once we run this bit of code, we will be able to see that it successfully registered the cool Mario model, and it waits up to 300 seconds. We don't need to worry about it because the model is registered much more quicker than that. And we get a nice configuration or a confirmation message that it was able to create version 1 of our model, cool Mario model. Next, if we are a little bit more proactive in logging or registering our models, what we can do is use the log model function or the log model API within MLflow's Python package to log and register the model simultaneously. So doing both at the same time. And this is best done from the train.py script directly after training. So instead of saving the artifacts or logging the model as an artifact, we can log it as a directory. And when we log it as we register it as a model. So instead of logging it as an artifact, we register it as a model, and that will basically make the entire process a lot more end-to-end. So if I open up our training script and go to line 144 as instructed, I see the actual log artifact path, right? And I can replace this with the log model API call. And in our case, since we are using a TensorFlow model, so we call the TensorFlow version of the MLflow API and log model as input. We provide to it the model that is there up here that we have defined and fitted to our training data. We set up the artifact path. So the artifact path is the same as the path that we specified right here, which is the models directory, and a name that we want to use to register our model with. So the registered model name, in this case, is Ultimate Mario model. Could you please mute? Okay, thank you. Okay, so over here we have our log model effectively done. That is all the changes that we have to make within our training script in order to register it as a model directly during our training process. So if I run this training script and it's basically the updated version of it, in a quick second, we will see the results of this entire process. Once the training is complete, we should identify the same information that we see over here within the register model call, right? The verbose logs that we get from calling register model in here. So it has completed evaluation, is still just as accurate as we last remember, which is unfortunate, but that's okay. And this saving the model itself, and we can see that it successfully registered the model and it created version 1 of model Ultimate Mario model. So that process is basically done. And now that we have gone through the two ways of registering a model, we can test out MLflow's search API. And we can do that by registering, by fetching all of the registered models that we have. So what I did over here is basically initialize the MLflow client once again. Within the client, I call the search registered models function and filter it by like percentage. So basically anything, right? And we get a list of models, and so we iterate through that list, and we get the latest version of the model. So we can, once we do that, we can see we have the cool Mario model as well as the run ID as well as the stage. We have seen that we have not defined a stage to our model correctly, which is why the stage metadata is set up as none. But besides that, we have all of the relevant information that we required exactly as we expected. Now, we'll perform a couple of specific queries on our registered model. For instance, if we want to specify models that have the cool, we can basically do that using by setting up the filter stream or the filter string with the function like attribute within the name metadata, and we will basically see our output as cool. If we want to maybe swap that for ultimate, we can do that as well very quickly, and it will identify and pull out all of the models that are prefixed by ultimate, and that's this one right here. So now that we know how to sort models that we have registered, what we can do is we can update the model information. So update information on models that we have already registered previously. Updating a model is obviously important. Besides being able to update the name of the model or the tags, possibly the most important attribute that you could update is that of the model stage. So let's start off with our basics, which is renaming a model itself. We can call the rename registered model function and set as input our original name. In this case, we will rename ultimate Mario model to great Mario model, and name and new name attributes accordingly, and that this should basically be it. We don't get any verbose output, but we see the tick, so I am going to basically take it as confidence that it worked correctly. Well, we will verify this in the future, but just for posterity. Anyways, so next would be updating the stage itself. So in order to update the stage, we can use the transition model versus stage function. And what we want to do is convert the great Mario model that is at version 1 to the staging stage. So from none through staging. And we can do this using the Python API. And if I run this, this will actually work. But we could do this, but I think it would be a lot easier to use the MLflow tracking server's web UI to do it, simply because it's just that much easier. So if you run this print statement over here, what it would do is basically construct the URI for you. If you like, you could also go through the repository itself under experiments and click on this button, and that will redirect you to this exact page. And once you do this, you would basically be able to see the interface for the Mario Wario experiment. And this experiment, you can see, has these 2 runs that we conducted. So the first run took 2.6 minutes. The second one was a lot shorter, and it also contains this model right here. So we can simply click on this model, and it should put up the interface for the model itself. We can see that the stage for this model is currently none. And if we want to update it, all we can do is just set it to production. And if you want, we can transition existing production models to archived. If you want to have multiple production models, that's fine too. We just disable that check. But here is basically what that does. And we have just updated the stage of our model using the GUI. We can do this for models that are not logged during a training run as well. So we can see that the model section for here does not contain our cool Mario model, which is the first one that we register. And The reason for that is we do not associate it to a run. We simply registered it separately. And we can identify or locate our cool Mario model, even though it is not associated with a run, by just switching to the models tab, and we can open that right here. And if we open this model and we basically pull out version 1, we can see that the stage for this is none, and we can update this as well if you like. So I can push this, and I will do that very quickly, and just like that, that is updated as well. Now, to verify that we have seen those changes, or we can see those changes over here as well, we can go through the cool, we can filter down the models that begin with the cool prefix, and we can see that the stage to the staging stage. And if I were to just let it print all of the models, I can also see the gray has been updated to the production stage. So since we are directly querying the MLflow remote, that update is all dynamic and anything. It is just there by default. In order to load a model, you need to first construct. So next, of course, let's talk about actually loading models that we have registered. In order to load a model, what you need to do is first construct the model URI that has the following format. So we have models : /the model name and the model version, or alternatively, you can set it to dynamically update by simply setting the model stage. So the name and the stage, you could set up the stage, and if you update your registry to set up a new model or a new version as your production stage, it will directly pull that one and basically update that dynamically. But for today, we'll just be using the model version call. So to basically get started with loading models, we specify name as Great Mario Model, the version as the latest version. So we call the get latest version from the MLflow API, provided the name, that is in this case Great Mario Model, and then we pull out the last one and pick up the version from there. We construct the model URI by basically setting up the format that we described above, and then load that model directly. Once that is done, we have our model instance set up, and that is basically the model that we have loaded from registry, not from the model that is present locally. So once we have the model loaded, we need to test it in order to make sure that it works, right? Of course. So we define this function to load a test image. We set a path for this image itself. We pick the image, load it, and perform some pre-processing. So basically convert the image to an array, normalize it, and expand dimensions. Once that is done, that's our image that can be directly processed by our neural network. And we basically provide the network the image for inference, and as an output, we will get the prediction that we get. That we will get our output prediction, which is basically the final sigmoid output. And it's the sigmoid output that we get is 0.45, which means that it predicts that this is Mario with very little confidence. It's quite confused because the value is very, very close to 0.5. However, this is actually correct since the image that we loaded was that of Mario. So I am very happy that worked correctly. But this is great and all. This is fantastic, and it will basically set you up for your Keras model, right? But what if you don't use Keras? What if you're a PyTorch fan, or the format that you use is not supported? Maybe you use your own custom framework that you have developed in-house, right? So there are many other supported frameworks, but what if you have a special case of your own? MLflow has support for generic Python functions as well. In order to support logging of generic Python functions, what we need to do is create a wrapper class that inherits from .pyfunc.python model. And within that, we need to extend this class to that takes the context as well as the model input and generates the output prediction. Optionally, we can also write a load context model in order to so this is basically almost like an initialization function that you can set up. So here we have an example wrapper. We have named this Mario model wrapper, and we're calling or we're extending the Python model class TensorFlow over here because really it is a TensorFlow model. But if you were using something else, you could basically use any arbitrary framework that you have set up, and it would work just fine. We within our load context function, we are setting up a model object that basically loads a model from the path of the artifact, and from there we're calling predict. We're calling the predict function. This basically does the exact same process as load image, except in this case for an arbitrary input. In our case, our arbitrary input needs to be converted to a buffer format in order to be interpreted correctly, and we do that by converting the base64 string that it will get as the input, simply because that's going to be the input that the REST API is going to receive, because that's how we transmit information over the web, or transmit binary information such as images over the web. We decode the base64 bytes into image bytes and create an IO buffer out of it, and that IO buffer can directly be processed by Keras's load image function, and that basically manages that input management pipeline. So once we have our input image, we can get the result by simply calling it on model, getting a list output and pulling out the actual value itself, and then we get the result as our or a numeric result output. So I will copy this example wrapper to our register pyfunc.py file, and that will set up the class itself, but of course we need to call it in order to be able to use it effectively, and for that it needs the following additional information. It needs the Python version that we are using to prevent dependency issues, and also needs environment information so that it installs all of the required packages that are relevant to the use case that we define. So by doing this, we can do that, and we simply basically copy all of this. We see that we use pip to install MLflow, Pillow, Cloud Pickle, as well as TensorFlow. We set this name as Mario_env. We can set it as anything arbitrary. It doesn't really matter. Once that is done, we also need to set up our artifacts directory. So we do that by setting artifacts and the path which we specify as our model directory, and that's basically the artifacts portion of it set up. So finally, all we need to do is instantiate the wrapper class and model itself. So we do that using this following bit of code. We set up our Mario model wrapper, pick an experiment ID. We've been working with Mario_Wario today, so that's basically what we will use. And we will begin our start. We will, using the start run within this experiment ID, we will log the model, set an arbitrary string over here, and pick the model itself, set the conda environment, the artifacts directory, and the registered model name. So this will register an additional model within this run that will contain the name Wicked Mario model, and it should basically set up the arbitrary class for inference that we can use that does not depend on the Keras backend. In this case, it does, because that is our use case, but you could basically swap that out with anything. So once we run that, it successfully registers the model that we had previously as the Wicked Mario model, and it creates version 1 of the model Wicked Mario model. So let's make sure that this has been registered by just running it, and we can see that we get 3 IDs or 3 models, and all of these 3 are the 3 that we defined sequentially. So we had cool, great, and the Wicked Mario model that we just have. And we can see that since we didn't define a stage, the stage is none, just like before. So now that we have done with that, we can save and commit our changes, because a lot of what MLflow does is associate all of the runs with a commit hash, and it allows us committing and pushing our code whenever we make a change allows us to ensure that the relevance or the association between the commit hash and the run ID is maintained. So it provides us additional context regarding our experiments. So in the event that our model does not work as expected, we could refer to the code that was used in order to generate that model and debug it accordingly. So finally, this is the coding aspect of our work done. And we have the deployment part of it to Amazon SageMaker. In order to deploy to Amazon SageMaker, there are 4 basic processes that we need to follow. The first one is to create an AWS account. You will need a credit card for this. Set up IAM roles and install the AWS CLI using pip. And this is the command that you will have to run. Next, please add your credentials to the AWS credentials. It's basically a config file that you will find in your home directory, and it should look something like this. Important thing is to make sure that you do not commit any of these into your Git repository, because from experience, I can tell you that that is a bad idea. The following, once you have all of that set up, you can run the following command, and you need to run it only once for each AWS account. You can run MLflow SageMaker and then build and push container, and that will create the Docker image that gets used by MLflow to serve the model, and that gets pushed to the Amazon backend. Once you have set up your container on SageMaker, in order to deploy it, all you need to do is know your SageMaker execution role and the AWS region you're going to deploy your endpoint to. And you set that up using MLflow SageMaker deploy. Set the app name. This can be arbitrary. The model URI needs to be the model URI that you basically wanted. And then you would provide information about the ARN regarding the role that you have set up, the IAM role, as well as the region name that you want to deploy to. Once that is done, that will complete the deployment to AWS, and you will be able to inference it and host all of their models and information with AWS. If you would like to create
Jinen?
a Docker image for arbitrary information, yeah.
Hey, Jinen, can you hear me? Sorry, I hate to interrupt, but we're going way over time, and we have a couple of people that are really interested in some questions that we want to get to, and then maybe we can wrap up after that.
Yeah, of course.
That's okay. Yeah, sorry, it's just we're just going a little bit over time here. So the big question that people keep asking is, people are saying that they're familiar with MLflow, but they want to understand better what the added value to MLflow is by integrating with DagsHub. I can say a couple of words on this, and if you want to take over after that, then you can do that. So I think the biggest thing you're going to see is that with DagsHub, you have your code, your data, and then you have your experiments all on one place. So DagsHub is actually providing you with the MLflow server that you don't have to set up yourself. We're taking care of all of that for you. That means you don't have to, provision a server somewhere, set up permissions and all that stuff, and then worry about security. DagsHub takes care of that. And this allows you to access your models and experiments from anywhere. So you might do local development on your local machine. You can still access your MLflow server on DagsHub. And then when you're ready to deploy, as Jinen was just about to talk, when you deploy to say Amazon or Microsoft or Google, those remote machines, those cloud machines that you're using to deploy to, can access the exact same MLflow server to grab the models to be used in production. This kind of integration allows you to just seamlessly do basically your entire experiment and deployment lifecycle all within one set of tools. So the other thing, I don't know if I'm allowed to say this or not, Nir, so please don't get mad at me if I do, but we are looking at adding a cool feature in MLflow, where with our integration with DagsHub and MLflow, where you can actually see what code generated a model or an artifact, which would be extremely helpful for reproduction if you need to figure out what went well or what went wrong with a particular experiment, and you're going back in time and trying to figure out what happened. Jinen, did you want to add anything to that?
No, I think that was pretty extensive. I guess the one thing that I would say is also the setup that is very, very often underestimated, especially if you want to set up something that is authenticated in a secure fashion, so that you prevent malicious users from basically exploiting the information that is present on your tracking server, especially for complicated projects that are in deployment. A lot of the information that is stored is extremely private. So it becomes a very significant overhead to maintain and ensure the security of the information within the MLflow remote, especially if you want to collaborate between a large set of users. And that entire access management is set up by DagsHub, which is where the added value comes in.
Yeah. Wen Liang is also asking, they want to know where the backend database and artifact stores are located so that they can access them directly if they set it up. Did you can you show them through the website? So if you take your repo name on DagsHub and just add .mlflow to the end of it, right?
Yep. And that will give you the actual MLflow UI.
Yep. That you might be familiar with if you've ever run MLflow servers yourself, and from here you can access the stuff directly.
I see the point.
Where can I see the commit info within MLflow? I need to access the Postgres, SQL, and S3.
So the commit information, I believe, should be within the DagsHub UI. Just update. PostgreSQL and S3, since everything is done through the MLflow proxy, so this basically uses the artifact proxy, which means that the direct URL to the S3 and PostgreSQL servers are not publicly visible. If you set up DagsHub on-prem, then you would definitely be able to just directly access the PostgreSQL and S3 bucket if you would like to do so.
Yeah, and let me just add to that. Maybe Wen Liang, if you can contact us on our Discord support channel and discuss what your use case is, maybe we can work with you to see what we can do there.
Absolutely.
It'll help us better understand the use case.
Sweet. Do we have more questions?
I'll just post the link to the Discord in the chat. Let me see. Is there another question? I lost my list of questions. Here they are. Okay, so Robert is asking, are DVC and MLflow complementary, or are they both attempting to solve the same use cases at this point?
I believe DVC and MLflow, well, they definitely overlap to a certain extent. If you're storing artifacts like your models, there is a significant amount of overlap. But the area where DVC really shines is the fact that it allows for very efficient data set versioning. You can set up branches of data and have or check out any version of data that you believe is for your given use case. I think that there is a lot of additional value in that rather than just storing it as an S3 directly, because that way you basically lose all of your version information. In the future, it is not possible to do that. Additionally, ML is to store data sets as artifacts. It is used to store outputs of your training sequence. So stuff like the output model or any training from your training sequence. Because of which, I think that DVC and MLflow are definitely complementary a lot more than they overlap. Does that make sense?
Okay.
Or am I? Did I cut out?
A little bit. You cut out a little bit. I understood. Well, I don't know if I understood because I understood the difference, but beforehand. So, do you have like a one sentence blurb that you want to just end it with?
Yeah. So DVC and MLflow are definitely complementary. DVC allows for dataset versioning, while MLflow is generally used for logging information regarding the outputs of your training runs. So that is the primary difference and where they complement each other very effectively.
Perfect. Okay. That was all of the questions we have so far.
Okay, awesome. So I definitely recognize that we're gone way over. It's 2:20 for just a little bit. I would like to talk about deploying or creating a Docker image and running the inference from MLflow. So that we can also use the Docker image anywhere we'd like. So in order to do that, it's a very, very straightforward set of commands that we need to run. MLflow models build Docker, then provide as input a name that will be the tag of the Docker container and set up the model URI. So your models and then the model name as well as the version, exactly like we discussed previously, and that will basically create the Docker container for us. In order to run the Docker container, all we need to do is set it up to run as a daemon, port forward 8080 to our local 8080, and pick the latest tag for the Mario Docker container. And that will set up the Docker container as a daemon, and it will be ready to receive requests. We can run inference using our Docker container with the curl command. The image input that it will take will need to be a base64 encoded image, because that is how web requests transmit binary data. But we cannot just send it as a base64 string. We need to encapsulate it in a dictionary, and as the key for our dictionary would simply be inputs, and we provide the value as the base64 encoded representation of the image. And here is a sample bash command that we can use, which uses the built-in base64 binary to convert our image into a string. We call curl on port 8080 with the invocations path. As a header, we set the content type to accept JSON data, and for our data itself, we would set the inputs key with the value as base64 encoded version of Mario_0.jpg, and it will give us the resultant output. That basically covers our Docker container. I also have set up a couple of typical errors that you could see. So this is just a bit of a reference for you guys if you think will be relevant, where there are a couple of errors that run into very often, and the solutions that you could use in order to make sure that it is not a. So that is all I have for you all. I hope you had a good time. Thank you for stopping by. If there are any more questions, I'm here to answer them. But yeah, I hope you all have a fantastic